more slowly, such that even if they wait infinitely long, they still never see the green person, if you like, age past this event here. Okay. This is the same kind of thing you find for a black hole. In fact, it turns out it's because it really is this problem.
Now, excuse me.
Tony, yes?
Is there a big difference between this and black hole in your opinion? The same in the sense that the yellow observer, the guy in the rocket, can always turn off the engine. And in fact, if he or she wanted, you could even go the other way and meet up with it.
That's right. That property turns out to fail in the black hole.
Right, because in black holes you can never go find the person.
Well, yes, you can.
You can. I mean, you can fall in also.
Yeah, you can fall in.
You can fall in also, but in this case, the person can't go back.
No, you can't. No. Look. Okay, the person could turn off their rocket and cross the horizon.
Right.
But they will never, even if they turn their rocket back on, they will never cross the horizon the other direction.
Right, so it's just the same.
So it's the same in that sense.
Mm-hmm.
Agreed, there are differences we can talk about later. But in this sense, it is very much the same. And in fact, the important point that I will get to, well, I might get there in a minute or two, but more likely next time, is that in fact, in the region close to a black hole horizon, it is exactly this problem. So I'm telling you now, and we'll see a bit more mathematically later, that if you really understand this example, you do really understand almost everything about a black hole horizon, at least at the classical general relativity level. So this is the picture to keep in mind. Just understand special relativity. Think about the light signals traveling. And in the end, you'll be able to translate to the black hole case. Of course, why this is the same as a black hole, or how this turns into a black hole, is a very interesting question that I have not yet explained. Yes?
That looks very similar to a light cone that you've drawn.
It is a light
on
cone.
the board there. But where your asymptote is next to the light cone, isn't that the area where you're traveling faster than the speed of light?
Isn't that what, sorry?
An area where you're traveling faster than the speed of light. You say that person...
So if I've drawn this properly, this yellow line asymptotes to the light cone, and its velocity keeps getting larger and larger and larger, and is asymptotically c. Now, my drawing obviously has a certain inaccuracy to it that may not have displayed that feature properly, but that is the correct answer. Okay. In fact, the correct answer is, as I will say in a moment, that the equation for this world line is that it is in fact a hyperbola with asymptotes given by the two light rays. Okay. Other questions? Okay. So you all see now that, in fact, this red line does have the properties you may have heard of for a black hole horizon. You can't cross it. You can't send information out from it. Okay. You may still feel this example is somewhat silly because it doesn't seem like it could be a black hole, but yes.
They asked some questions, but I would just like to know the second light ray that you drew on that graph, is that traveling negatively in space?
It's traveling in the opposite direction. So there are two light rays that go out like this. Okay, yeah. And someone called this a light cone. That's an accurate story, except that so far I'm working only in 2 dimensions, so there's not much of a cone to it. It's just 2 light rays that go out. Okay. And I'm doing that intentionally. And that's not a simplification. The right analog for a black hole is the light rays in 2 dimensions, in a way that I'll say in a moment. Okay, it's not quite a light cone in 4 dimensions. Okay. All right. Let's see. Yes. All right, that's our qualitative story. Did I do the redshift part? I guess it's the same thing. Just as in George Ellis's lecture this morning, as we said, if this green observer is emitting flashes of light, the yellow observer receives them more and more slowly. And therefore, if these are not flashes of light, but the oscillations of some uniform frequency that the green observer is emitting, if the green observer is emitting, say, green light, and these mark all the peaks being sent out in the light wave, then the rate at which the peaks arrive is slowed down for the yellow observer, and therefore the yellow observer finds that radiation to be redshifted, to be at a different frequency. And the redshift clearly diverges as we move up the yellow world line. Okay. And again, the same property happens for a black hole. Okay. Good. All right. So now, I'd like to try to introduce So we read all those properties off of this picture. Okay. In order to move to the black hole case, I'd like to introduce a slightly more quantitative description of this effect and these observers. Okay. So I'm going to need to write down some equations. Right. Because what I want to do is go back to, go back here. We agree this is the fundamental equation that describes the fact that we're in Minkowski space, right? But this equation is written down more or less assuming a certain point of view. dx and dt are coordinates that are really naturally used by inertial observers. T is something whose slices go like this. X is something whose slices go this way. Okay. What I wish to do is rewrite this equation from the point of view of not the inertial observers, but these uniformly accelerated observers. Okay. And that will allow me to transform into the black hole case. So what we want to ask are the questions of in what way would it be natural for these uniformly accelerated observers to measure time and distance? Okay. It turns out that to answer that question, it is nice to first understand what is the equation for this world line. And I think I'm just going to write down the answer for you today. Perhaps this should be the first homework problem for your workshop period. But the answer is that, as I briefly mentioned, this yellow world line is in fact a hyperbola. So it satisfies x squared minus t squared is equal to some constant. And let us call the constant zeta squared. I guess that's a zeta. Yes. Okay. Or is it a xi? Is it a xi? All right, it's xi. All right, let's call it xi squared. Good. It's squiggle squared. Okay. Right. So since this is a hyperbola, a natural way to parameterize the hyperbola is through the use of what's called the hyperbolic angle. And I don't know how familiar you are with this, but I will mention that just like in trigonometry, where one can characterize a circle by a radius and an angle, hyperbolae can be characterized by this parameter xi and what's called the hyperbolic angle. And the equations are the things you might guess. One writes x as this xi times the hyperbolic cosine of the hyperbolic angle. And one writes t as xi times the hyperbolic sine of the hyperbolic angle. Okay. Now, I guess I should just double check. Usually when I get to this point with my undergraduates back in the United States, I find out that they don't know what these two functions are. So in case that's true for any of you, let me just mention that these are hyperbolic cosine is e to the theta plus e to the minus theta over 2. And hyperbolic sine is e to the theta minus e to the minus theta over 2. Okay. And, right. Good. And they have just this kind of property that, of course, if you square this and subtract the square of this, you get this, because everything cancels out when you expand in terms of the exponentials. Okay. Right. So, let's see. What I want to convince you now is that, in fact, the natural way for this yellow observer to measure distance is not using the inertial coordinate system. That is to say, the yellow observer would not naturally draw some line here and measure distance between two events in this way. Okay. Instead, the yellow observer would naturally use these lines like the one that I've drawn here. And they would naturally measure distance in this way. Now, why is that true? Well, you're probably familiar with the fact that in special relativity, observers, of course, measure distance along some line which is orthogonal to their world line, right? That's the line of simultaneity in special relativity. The phrase doesn't seem to be familiar. Okay. Da-dum-dum-dum. All right, let me do this a different way. Let's simply note that this formula here, the equation for that hyperbola, looks an awful lot like that formula up there for the proper distance. Right? So in fact, or even better, like this one before I took the infinitesimal limit. Even better, like that one. If I simply down here replace, if I write delta x is x minus 0, and delta t is t minus 0, then this equation and that equation become identical. Yes? Okay. So what we learn here is something interesting. We learned the path of a uniformly accelerated observer is a world line which is always, at any point, a proper distance xi away from the origin. Okay, in other words, even though this observer is accelerating, the proper distance between the observer and the origin always remains constant. Okay, an interesting effect. One that may, again, remind you of maybe of something about black holes. Okay. Therefore, let me do this very quickly. Suppose I put in not just one uniformly accelerating observer, but suppose I put in several. Let me add another one over here, whose asymptotes are the same light cone. And let me add another one over here, whose asymptotes are again the same light cone. Okay? Then what have we just learned? What we've learned is that the proper distance between this middle observer and the origin remains constant. We've also learned the proper distance between this leftward observer and the origin remains constant. Therefore, by a little bit of subtraction, one can convince oneself that the proper distance between these two observers also remains constant. Okay. So if this observer wished to measure distance by standing here in his rocket ship, doing his thing, actually imagine the rocket ship is accelerating this way. Okay. And then suppose that he wished to measure distance by, say, putting one of his friends 1 meter stick away to record all the events that happen 1 meter away. Okay. He would then build, let's do it this way. Okay. So we're accelerating upwards. I could then build a little platform 1 meter tall of constant proper distance and put one of my friends up there to measure all the things that happen at the top of this stick, which are 1 meter away. And I could also suspend on some sort of rope a platform below me with another friend who measures all the things that happen 1 meter below me. Okay? Well, what we've seen is that, in that case, the friend above me remains the same proper distance away. The friend below me remains the same proper distance away. So, and that same property is satisfied by these two world lines I just drew.